Hope the screen is also visible. Okay. Okay, so we were actually started discussing on maybe the basics of probability theory that is actually required to maybe as a prerequisite for understanding many of the other maybe pattern recognition techniques. Okay, maybe in the coming classes. So we will quickly go through some of the basics of this probability theory. And here so this maybe the details are actually explained with respect to an example, okay, taken from our textbook. Now, assume that we are having two, okay, say boxes. One is red in color and another one is blue in color with the apples and oranges. Okay, so the apples are in green color and oranges are in, say, orange color. Okay, so that is maybe the an example that will be discussed maybe throughout, okay, in the coming slides. So here we assume that okay, so we assume that we take some say random variables, okay, which can actually take a set of values. So in this example, we assume that these random variables take actually discrete values, but this can be always extended to continuous variables also. That means that variable, random variable, can take any value, okay, any real value. Okay, but in this case, as these are discrete values like apples and oranges and boxes, okay, we'll be limiting our discussion with respect to discrete space. Okay, so that is one point. And this is maybe give an explanation about maybe say so the different maybe the scenario. We assume that we are having okay two random variables. So assume that we are having just a moment. So is it visible? Okay, so assume that we are having two random variables, x and y, where x actually takes values from okay 1 to etc to m, and y, okay, takes values from okay 1 to etc to say l. Okay, so there are m different values, discrete values taken by the random variable x, and y actually takes l different values. Okay, so that is actually maybe you can say that okay, here along the horizontal direction we are having xi, okay, so which is individual values of x, and along the vertical direction we are having yj, okay, so the individual values, discrete values of the random variable y. Okay, so here we can say that m is equal to 5 because x takes okay 5 different values and y takes 3 different values. So L is equal to 3 maybe in this particular example. And so if you look into this, maybe one value, okay, specific value of xi. So that means a random variable x actually takes a particular value xi. So for example, let us say for example, x actually, okay, representing the eye color. Okay, so eye color of a person. So that can be say you have black, okay, say brown, or say for example some other things, gray or whatever things. So that means they are going to be the say different values. Okay, not 5 different colors, maybe just example. Okay, so they can be the different values, and y can also be another random variable or another feature. So that can take maybe another set of say discrete values. Okay, so here so this particular xi column, okay, if you look into the xi column, so that actually represents okay so the cases, okay, all the cases where the random variable x takes xi value, and in correspondingly for that particular value y can take okay 3 different values. So can be y1, say y2 and y3, okay, whatever is the case. And the total number, okay, maybe in such case for okay xi, okay, with respect to a random variable x is actually ci, that is count, okay, of maybe say that particular case where a random variable x actually takes xi value. Similarly, if you look into y random variable, okay, so let us say that rj is actually, okay, the total summation, okay, where say the random variable y takes okay, so the value, okay, say jth value, okay, so that is the case. And if you look into the cell value, okay, where it is written ni comma j, okay, so that actually represents maybe the how many times, okay, x take xi and y takes the value of yj. So that is going to be the count of maybe the frequency, okay, okay, of maybe the different scenarios or trials or whatever we call in probability theory, okay, or the number of instances, okay, out of which, okay, x takes xi and y takes yj. So that is actually the meaning of maybe nij. That is a number of, okay, instances or trials or frequency, whatever it is. So that is actually the maybe the scenario, okay, so that is very important. And now what we can do is, okay, so if you look into maybe the previous diagram, okay, so we can actually define, okay, maybe say a joint probability, okay, so which is actually we call as probability of x comma xi and y is equal to yj. So that is what we were discussing. So that is the we know that the total count is actually nij, okay, according to the previous maybe the cell value or the diagram. And the total, we assume that there are n instances or n trials or whatever it is, okay, so that is nij divided by capital N is actually uh, the probability, and we call that is a joint probability of, okay, x and y, okay, for a particular say values taken by x and okay y. So that is a joint probability. And now comes suppose we are having probability of okay, x is equal to xi. So that means maybe with respect to the previous diagram, this particular case, so that is the x actually takes value of xi. So if we consider all such possibilities, okay, we can say that the total, okay, frequencies or total instances in such cases are actually say ci, okay, and so that means ca divided by total n. So because among all the possible, okay, cases, we have a ca divided by n is actually the all the cases where we have a x actually takes the value of xi. And you have to note that this is irrespective of y, okay, because we are not interested in what value y actually takes, but we are interested in only in maybe this particular case. And so that means okay, if you look into that previous say cell representation, then we can say that is ca is actually, okay, we have to take all such summation of all such nij values, okay, where we have to sum it over for all the j, okay, so that means 1 to l. So that means we have to sum it over all the different values taken by the y variable, keeping it the same xi value. So that is actually this representation, okay, means. So that is actually the idea of maybe that probability is actually called okay, marginal probability, okay, so that is this particular probability is marginal probability. That we will, okay, see, okay, and this is a joint probability, okay, so that is just we have seen. And so now what we can write is from the above two maybe results, okay, we can say that okay, this probability of, okay, x is equal to xi is actually because if you substitute, okay, this particular summation, okay, into, okay, that will result in this particular say result. So that is j is equal to 1 to l, because we have to sum it over all the that entire maybe the vertical columns, okay, where we have x is equal to xi and y is equal to yj. Okay, so x is going to be fixed and y will vary. So that means that is going to be the summation of the joint probabilities. But that joint probability is actually summed up for individual rows, okay, maybe in this particular case. Okay, so that is a way we can represent maybe probability of, okay, x is equal to xi, okay. And then we can say that the probability of x, okay, so here we what we have a written is actually we have written the specific cases like x is equal to xi, y is equal to yj, but we can just ignore those specific representations, and it can be written in a general fashion, okay, in this particular equation, which is same as the previous equation. So that is probability of x is equal to, you have to sum it over y, okay, okay, the joint probability of x comma y. So that is the same equation, but maybe the component wise or the individual maybe values are ignored, but we have written in a general variable fashion. Okay, so that is x and y alone comes, that is random variable x and random variable y alone is actually used in the notation. Okay, and this is sometimes called the margin probability, but famously it is actually called, this is called the sum rule of probability. Okay, so that is most important, because we have maybe a sum rule and a product rule, okay, in probability, which are going to be used, okay, throughout our maybe discussion or in the coming classes. So that's why we are actually just going through these fundamentals. So that is a sum rule of probability. Okay, because it actually represents a summation, okay, over the different values of, okay, or the discrete variable y, okay, for finding out the margin probability, okay, of the other random variable x. So that is actually the interpretation. Okay, we'll come to an example later. Okay, but before that we will just go through some of the other, okay, this notations and maybe basic concepts. Then I think you know about the conditional probability also. So here we are actually assuming that okay, it is given that x is equal to xi, okay, and then we have to kind of find out what is the probability that okay, y is equal to yj. So that is a conditional probability, and we know that here x is equal to xi is actually the case that we have to maybe consider. Okay, so that means we can say that okay, that probability is actually nij divided by ci. So that is the total cases are actually x is equal to xi, that we know that that is a ci. And then what is the probability that y will take maybe, okay, so that means if you look into this particular maybe column, okay, so I already know that x is equal to xi is given, so that means we have to look into only that column. Okay, and then what is the probability that y will take maybe different values. So that is maybe this particular case. So that is why this probability is nij, okay, divided by ca. That is called the conditional probability. Okay, so that is another relation, so another result that we have. And now if we go back to this joint probability, so that means probability of x is equal to xi comma y is equal to yj, and we know that that is nij divided by n. Okay, maybe from the previous equation. Okay, and we can actually maybe rewrite that equation in this form. Okay, just we are rearranging in the sense that maybe nij divided by ci into ci divided by n. Okay, so it is same as nij divided by n, but why we are actually bringing that particular maybe representation is, okay, in order to maybe derive the product rule of the probability. And nij divided by ca we already know that is this particular conditional probability, and ca divided by n we already know. Okay, so that is ca divided by already know, that is actually the this margin probability. So that is probability of x is equal to xi. Okay, so that is we can say that the first one actually corresponding to this one, and the second component corresponds to this one. Okay, so that is we have a product here. Okay, so that means we have the joint probability, okay, is equal to the conditional probability into the marginal probability. So that is called the product rule of probability. Okay, so these two results are actually very important. Okay, so that we will maybe that we will see, okay, in many derivations or main discussions maybe in the coming classes. So that is a two very fundamental rules. I think you might have already studied this one, but we are just going through quickly. Okay, the basics. So that is one thing, and now we will go to, so the second one. Okay, then So this is a compact notation. So that means the product rule can also be represented in a compact fashion. Okay, that is we are just ignoring the components. Okay, but we are representing only the variable. So it is a random variable. So that is probability of x comma y is equal to probability of y given x into probability of x. Maybe just we have a okay C. And here we the individual terms are, we can say that probability of x and y, that is a left side, okay, of this equation. And the first part on the right is probability of y given x, okay, and maybe the last one is probability of x. So that is the case. And now we can have we know that according to the symmetry we have a maybe probability of okay x given sorry probability of x comma y, that is a joint probability of x and y is equal to probability of y comma x. So that is okay, uh, that is there. So that means accordingly we can write a probability of y comma x. Okay, maybe okay we have a probability of x given y in the probability of y, and using the equality that we have just seen, we can write this equation like this one. Okay, and then from there we can actually derive a probability of okay y given x is equal to probability of x given y in the probability of y by probability of x, and which is the very famous okay Bayes theorem. Okay, that you might have studied okay during your UG course. Okay, and this is a very important okay has to play a very important role in pattern recognition or ML systems. Okay, so it's Bayes theorem because we will see a class pattern recognition techniques using Bayes theorem. Okay, so that is a significance of maybe the Bayes theorem. So that is a maybe another point. Okay, then using the sum rule. Okay, using the sum rule that we have already discussed. Okay, so here the probability of x is actually the denominator. Okay, in this particular Bayes theorem, we have probability of x as a denominator, so that can be okay maybe represented like this one. Okay, but if from the using the sum rule we can say that we are summing into our okay the random variable y probability of x given by into probability of y. So that is a result that we can derive okay from the sum rule and maybe using this equation. So you can say that if you look into this Bayes theorem equation, so the denominator is no is nothing but a normalization okay constant. Okay, so that is to ensure that the total probability is going to be maybe one. Okay, because here we are actually looking for okay you are given a particular x, then we are summing it over, suppose we are summing it over different values of y. Okay, so in such cases the probability must be okay the total probability must be one. So in order to ensure that we have this denominator, okay, so that is going to be the case that is placed like a normalization constant. So that is the significance of maybe Bayes theorem, okay, and related things. And then we will go to okay, so now we will just see an example. Okay, so far we have seen the sum rule of probability, the product rule of probability, maybe the joint probability, okay, marginal probability, and then we have seen the Bayes theorem, okay, etc. So we will see maybe how maybe a particular case, okay, will look like. Okay, so suppose we are having okay x alone, okay, that is a random variable x takes nine different values, and random variable y actually takes two different values. Okay, so we have m and l okay is equal to 9 and 2 respectively. Okay, so that is a joint okay distribution of probability of x comma y. Okay, so these blue dots are actually representing the data points. Okay, so corresponding to different x value and different y values. Okay, so that is a top left figure represents. Okay, so that is a it is a distribution of the two variables. So that means how these values of the probabilities are actually maybe lying for different values of x and for different values of y. So that is the idea. Okay, and and if you look into the top right diagram, okay, that represents the distribution of maybe probability of y alone. Okay, because we know that the probability y actually takes two values, y is equal to 1 and y is equal to 2. So how many points are actually are actually with the probability of y is equal to 1, and how many points are actually with the y is equal to 2? Okay, so that is actually that particular distribution, okay, represents it. And similarly, if you come to the bottom left, okay, diagram, so that is this diagram, we can say that that is a distribution of maybe how the values of x actually falls. Okay, so how many are actually there with the maybe x is equal to 1, x is equal to 2, x is equal to 3, etc. Okay, so that is a distribution of maybe probability of x, okay, in this cases. And now the bottom right diagram, okay, this is a very simple example, a specific case where we are assuming that y is equal to 1. So that means this particular case, okay, y is equal to 1 and different values of x. Okay, that is probability of x given y is equal to 1. So how the distribution will look like. So these are actually maybe the conditional distribution. Okay, we know that the conditional distribution, because y is equal to 1 is already given, and we have to find the different cases for different x values. Okay, so that is a way how maybe a probability distribution. Okay, in this case we have a discrete set of values that can be looked into. Okay, maybe because in the coming discussions we will be just mentioning that okay, it's a discrete variable, then the probability distribution. Okay, then this example will help you to maybe identify maybe how we may have to approach that particular maybe situation. Okay, so that is actually the case. And so now we will go to the next one. So okay, so this now what we will do is we will just go through the previous example that we started with the apples, oranges, okay, red and blue boxes. Okay, and so here we will see how we can apply the previous equations that we have just seen. Okay, maybe for an example with respect to an say example. Okay. So here we have already I have already mentioned that okay, or just to keep in mind that 40 percentage okay chance that the red what box is actually selected, and 60 percentage okay chance that we have the blue box is actually selected. So that means we have only two boxes, one is with the 40 percentage chance to select and the other one with the 60 percentage. So that means we can say that this probability, okay, that is probability of b given r, okay, is equal to 4 by 10, and the probability b given b is equal to 6 by 10. So that is a way we can actually find out those probabilities. Okay, and then there can be different questions that we will come across with okay, what is the probability that okay the fruit selected. Okay, as if that we are here we are having two random variables. Okay, one is the box and another one is the fruit, so we represent using okay b and f. So keep in mind that these are similar to maybe say x and y that we have just discussed okay in the previous slides. So any there can be x y z, there can be maybe n number of maybe such features or say random variables that we can actually consider and extend the discussion. Okay, and here we assume that maybe say for example you're saying that the box selected is a red, what is the probability that okay, fruit selected is apple, that is the probability of f is equal to a given b is equal to r. So that is we can find out that one. Okay, so that is these results are actually taken according to maybe so for example if it is red means we have a total 8 number of fruits, okay, and out of which 2 is actually apples. So we have 1 by 4 is a probability for okay the first conditional probability. Similarly we can find out the conditional probability for each of these cases. Okay, so that is a, and so this is just an application of what we have just okay maybe seen the results. And similarly we can say that okay we have only two boxes, okay, two, okay, so that and only two I mean the fruits also. So that means we can say that they are they should sum to say 1. That is probability of, suppose we are taking a red box, then it can be either apples or oranges. So that means probability of f given f is equal to a with maybe so that is we have a okay f is equal to a given b is equal to r plus probability of f is equal to orange, okay, fruit is equal to orange, box is equal to red, so it should sum to 1, okay, because we don't have any other maybe case. Similarly we can say that a blue box also, okay, it should sum to 1. So these are the entirety, okay, the case that the example that we are having. Now similarly, okay, suppose we would like to find out the probability of say fruit is equal to apple. Okay, suppose we are randomly picking a fruit from any of the boxes, and then what is the probability that the fruit is equal to apple? Suppose we would like to find out an answer for such cases. So that means here something like a marginal probability that we have to find out for f is equal to say a. Earlier we have seen the equations for probability of x is equal to xi. Okay, so that is that way we can find out maybe apply that previous to this particular case. So we can say that probability of f is equal to a, okay, b is equal to r in the probability of b is equal to r. That is one possibility, and another one is the probability fruit is equal to a but box is equal to b in the probability of b. So that is we have to take a summation. So that is a maybe so that means we are actually summing it over different y values, okay, because y can take it here y, let us assume that this is y, okay, and this is say for example x, okay, so in such cases the previous equation we are just applying here, so that you will get a probability of say maybe say in this particular case 11 by 20, okay. And we know that suppose we have to find out that what is the probability that the fruit is equal to orange in the same scenario, okay. So once you have found out this one, we can say that the total probability must be for selecting an apple plus probability of selecting an orange, they should sum to 1, okay. So that means we can say that we can find out 1 minus, okay, 11 by 20 in this particular case, that will give you the probability for fruit is equal to orange. So that way we can actually maybe apply, because the total probability is actually 1. And similarly what we can do is, okay, so here now let us say we go to the condition probability. That means assume that the fruit is selected as orange, okay, but what is the probability that it actually maybe came from the red say box? So in such case, how we have to represent the probability? Okay, probability of b is equal to r given the fruit is equal to orange. So we can apply the base theorem, okay, and we'll get the probability value. Similarly, maybe the other way, okay, that is we know that the fruit is orange, but in the first case that we have calculated is for box is equal to red, but what is box is equal to blue, then it is actually 1 minus, because where the apples as oranges you can select only from 2 boxes, so we can just subtract the previous value from 1 to get the remaining. So this is a way we can actually apply a specific okay example. So here another so few terminologies that we have to see, okay. So one is actually a prior probability, okay. So the prior probability is, let us suppose that you are given that the box, okay, say for example we are actually calculating your box is known. That means you have to say that the probability of selecting an apple, okay, from a particular case, okay. So in that case we know that the say before we observe apple, okay, we know that the a particular box is actually selected, okay. So in that case the probability available before we observe the identity of a particular case, that we call it as a prior probability. Okay, so in this particular case, okay, suppose the box is already known, okay, and then what is the probability that okay, the fruit is actually apple or orange, whatever it is. Okay, so that probability is actually called a prior probability, because it's a prior we know that particular case. This is a very important maybe concept, okay, and that will be applied maybe when we discuss the classification, okay, using maybe base, okay, maybe principles. So that is another concept, and
Sir, can you please explain this prior probability?
Yeah, prior probability. Suppose you assume that you are given say you have some prior information about a particular say event, okay, or say particular case. So in this case, assume that we are actually trying to find out the probability of maybe say finding out a fruit, okay, but we know that there are another random variable where we have a say box is there. So but we know that particular probability, okay, before maybe observing or before we taking a fruit from any of the boxes. That means say for example 4 by 10 and 6 by 10 in this case. So in this case, that particular probability is already known. Suppose there can be a situation that you don't have that information is also not there. So in such cases we will not be able to define that prior probability, okay. So, for example, in the sea bass and the salmon cases, that is the fishes that we have example that we have discussed. There can be say, suppose you know that so there is a prior probability that salmons, okay, appearing in this particular case is in this particular location, okay, or particular period that we are actually considering has got a particular probability, okay, or in the case of a say a disease, okay, in some cases suppose a domain expert knows that okay, this is a probability, okay, which is a rough value, okay, maybe from domain knowledge or from the maybe available data also you can maybe calculate what is the prior probability, etc. So that is a concept of prior probability, okay. Okay, so that is a case. And um, we have another probability called a posterior probability, so which comes after, okay. So that means it is actually coming after we have observed a particular variable f. So that means that is we know that f is already okay observed, okay, and then what is the probability that okay the box is actually maybe a color or maybe a second variable is of maybe particular value. So that is called a posterior probability, okay. It is come after the we have observed that a particular okay value for a particular say random variable. So that is actually the case of posterior probability. So that we will discuss maybe or we'll apply maybe in detail in the coming discussions. But these are two important terms that we have to always keep in mind, okay. Then there is a maybe a result. We suppose we are having x and y are say two independent okay say random variables. Then we can say that the joint probability value okay is equal to probability of x into probability of y. So these are some of the results and some of the concepts that should be maybe aware of, okay, in order to have a detailed understanding about the further maybe say concepts. So that is actually about maybe basics. But now we have some other concepts also we should study, okay. These are some of the things that so Bayes theorem also we have, okay. So this is something that we will discuss later. That is the Bayes theorem can also be maybe written something like this one. So that is a posterior probability is equal to, we call it as a likelihood into prior. So that we will not go into the details right now. We will see the thing when we discuss Bayes theorem, okay. So what is going to be discussed in the next class is we have to look at, so far we have discussed about the discrete cases, okay, but the same can be extended to continuous okay valued variables also, okay, any real value, okay. So that means we'll have to consider an x okay value and maybe express delta x, a very small change, okay. So in such cases we have to define probability density values, okay, probability density functions, their distributions, etc. So I think that we will discuss in the next class, okay. So today we will wind up with this one, okay. So thank you for listening, okay. So we'll continue with it tomorrow.
Yeah, thank you, sir.
Okay, thank you.